space friend, it's about time we fix some mechanical problems on this ship, don't you think? Today we're going to do that using servo motors. Servos have all kinds of uses like robots, automation, or industrial equipment. They are AC or DC motors that give you precise control over rotation and position. An AC motor handles higher current, so those are better for industrial machinery type things. DC servos are not made for higher current, so these are better for low power projects. They still drive a considerable amount of power though, so if you plan to use more than 2 servos at a time, it's better to power it through an external power source instead of just the 5V pin on the Arduino. Servos typically have 3 wires, one for power, ground, and signal. The power wire is typically red and gets connected to 5V on the Arduino. The ground wire connects to ground and is typically black or brown. The signal wire gets connected to a digital pin on the Arduino and is typically yellow, orange, or white. A servo usually has a motor, control circuit, and potentiometer. The resistance of the potentiometer changes as the motor rotates, allowing the control circuit to regulate the movement. Servos can rotate clockwise or counterclockwise, usually 90 degrees in either direction for standard types. Continuous rotation servos allow the rotation of the shaft to be set at various speeds. The direction that it rotates is dependent on the signal that it receives. Servos are controlled with pulse width modulation. The PWM signal sent to the motor determines the position of the shaft based on the duration of the pulse. The servo translates the width of the pulse into a physical position. When it's instructed to rotate, the motor is powered until the potentiometer reaches the value given. Once it's been moved, the servo holds that position for as long as the PWM signal commands it to, or you knock it out of the way with brute force, I suppose, but that'll probably damage your motor. Servos have an encoder that determines its rotational position, and then uses this information to perform feedback control of the motor's position. Feedback control is a way to minimize errors. The control variable is measured and compared to a target value, and the error is the difference in the actual and the desired value. Feedback control manipulates input in order to minimize the errors. With servos, this means they have precise stopping accuracy. Today we're going to fix the ship's solar array positioning because that's a real thing that servo motors are used for. First, we're going to control the servo with the potentiometer. We need a servo potentiometer, a breadboard, and 8 jumper wires. I've got one quick thing before we get to the code. Either I'm the dumbest person in the world, or this is a classic example of non-beginners forgetting the kind of things that beginners get confused by. So when I bought these servo motors, they come with different attachments you can put onto it. It also comes with screws, so I assumed I was supposed to screw it on here in some way. I could not figure out how to do that, so I scoured the internet looking for someone to tell me, how do you attach these two things? But I could not find anything telling me how to do something so incredibly basic. So for the handful of people as easily confused as me, all you do is pop the little bitch on. Nothing more to it than that. First, we have to include the servo library. You can find that by going to Tools, Manage Libraries, and then searching for the library called Servo. My servo is creating oh, servo, my servo is creating a servo object to reference our physical device. We're creating 2 variables, one for the potentiometer and the other 2 hold the value read in from the potentiometer. In the setup, attach is how we set the servo to a pin. 9 in the parentheses means that we're attaching it to pin 9 on the Arduino. There are an additional 2 optional parameters with the attach function min and max. Min is the pulse width in microseconds corresponding to the minimum or 0-degree angle of the servo. The default for that is 544. Max is the pulse width in microseconds corresponding to the maximum or 180-degree angle on the servo. The default is 2400. In the loop, we're reading in the state of the potentiometer and then mapping that value to a servo position. An analog reading of 0 is mapped to a 0 rotational position, and the maximum analog value for the potentiometer of 1023 is mapped to the 180-degree position for the servo. Then to actually send that value to the servo, we do servo.write. So we're starting the potentiometer off in the 0 position, so it's doing nothing. If we turn it slightly to the right, servo does the same, back to 0, and then when we turn it to the left, it goes around the other way. Whoa! I'm not really interested in always needing to fix the solar array manually, so let's see how to control the movement without any additional input from us. The only thing we need to change for this project is to remove the potentiometer and connect the servo directly to the Arduino. We're starting off similarly with including the library and the servo object. Then we create a variable for position and the servo is still attached to pin 9. In the loop, the 3 parts of this for statement are an initialization, a conditional test, and then what needs to happen for the next conditional test. So while position equals 0, if position is less than or equal to 180 degrees, add 1 to position. So we already know that we're starting off at position 0, so the conditional is true. 0 is less than 180. So position is going to increase from 0 to 1. Then it's going to continue doing that until it reaches 180. Then we'll write the value of the position to the servo to make it actually do the work. The next for loop is how we rotate it back. While position is 80, if position is greater than or equal to 0, decrease position by 1. Then write the value of position to the servo. This loop will make the servo rotate 180 degrees back and forth until you remove a power source or you break it. But I've got enough broken in here, so I think we'll just unplug it. Well, that's fun. Solar array positioning fixed. You'd think that's something I would have got around to way earlier.